Welcome to Vegas. Welcome to reInvent 2025. You are in ANT307, operating and scaling managed Kafka and managed Apache Kafka and Flink. My name is Ashish Palekar. I take care of our Kafka, Flink, and Firehose services here at AWS, which means that I spend time talking to customers, but also building the service, but also operating the service. With me is
I'm Sai Madali. I lead the product teams for our Amazon Managed Streaming for Apache Kafka, our managed service for Apache Flink, and Amazon Data Firehose.
Very cool. So today, we are going to cover a bunch of what we are doing with our Kafka and Flink services. We're going to walk you through our learnings and compare and contrast, give you a sense of what we've learned, and hopefully we can cover a lot of details in the session. So let's get started. As we go through it, a lot of customers often start with why streaming data and why now. It really boils down to four things that we hear from customers. It's about unlocking real value from your data in real time as it flows, helps you make decisions in real time and shorten the time to actually get to insights. You can get continuous intelligence from that data. And last but not the least, as we are continually seeing now with AI workloads, you need more contextualized data, you need more fresh data, and streaming technologies help you get that. Here at AWS, we love Kafka and Flink. We've had a Kafka service. We have had Kafka and Flink services for well over 5 years at this point, and in fact have been operating workloads for customers. We have customers who also use self-managed Kafka and Flink. In addition to ours, and there's certainly other partner solutions as well. But really, we see a large and wide variety of workloads across the board. So one of the things I get asked by customers is, what are the outcomes that customers look for when running at scale? What do customers really care about? It really boils down to price performance, boils down to reliability, boils down to security, and boils down to performance. These seem like basics, but at the same time, at scale, these are magnified. And every one of you that is operating a Kafka or a Flink service knows that. Just by show of hands, how many of you operate a Kafka service? Vast majority of you. Awesome. So that this helps Sai later on, how many of you use Flink? Few of you. We'll talk about that too. Thank you for being our customers. These are some other customers. Customers make our world go round, and this is absolutely super helpful for us to understand what customers are doing. So let's talk about running Kafka at scale. Always love to start with a customer example. Nexthink. Nexthink is a customer based out of Switzerland, and really focus on how to go build developer experience. Their core problem was how to help scale their Kafka business. Switch to MSK, they were running on premises, switch to MSK on AWS, and they can process now trillions of events a day, reaching 5 gigabytes per second of aggregated throughput. Really has been compelling to watch their journey in scaling from 200 megabytes to 5 gigabytes per second. And that is taught them as well as us a whole bunch of lessons. And as we observe workloads across our customers. So when we think about the spectrum of Kafka, we really, and I'll speak to sort of the services we offer, we think of it across a two-pronged spectrum, right? Like one, on the left-hand side, you have more Kafka control, and then on the right-hand side, you have more Kafka automation. In the more Kafka control case, we offer standard brokers for Amazon MSK. This is the case when you're migrating from an existing Kafka setup. You need fine-grained control for Kafka, and you know and have deep know-how about how Kafka works, and that becomes important. On the other end of the spectrum is Amazon MSK serverless, where you can quickly deploy and scale up Kafka. You don't need Kafka management, and you don't need or care about the nuances of managing Kafka. And in between, there's something we launched last November, is Express Brokers for MSK, where you value performance and elasticity, where you want or need lower control over Kafka. And typically what we see is this is a set of customers that is managing Kafka at scale. And this is something I provide as guidance to customers when I talk to them. Unless you know differently, always recommend you start from Express. It's a good place to start for your workloads and then decide where to go. So across this family of products, we see a diversity of Kafka workloads. And it gives us really, really interesting insights. We see customers operating at small scale, large scale. We see customers operating with a high partition count, low partition count, combinations of both. And that entails different things. One of the first areas that I'll talk about today is about storage management. And this starts to get tricky, especially at scale. Specifically, storage scaling takes time. And as we started looking at it, you can go from 4 terabytes to 8 terabytes to 12 terabytes. All of this is possible. One of the things we consistently see is customers who are not monitoring their storage utilization. In fact, your storage utilization can spike. You can start to see that grow as workloads change. If you haven't already, there's something MSK offers. You should subscribe to Disk Full Alerts. You get alerts at 60% full, at 80% full, and then when it's actually full. But that will alert you to make sure that your capacity is actually taken care of. One thing we noticed is it is easy to scale up capacity, but you don't have a capacity scale down. And that is something that trips up customers. And so customers often delay making a decision about scaling up. And it's something that is a tension that you need to wrestle with as customers. Recognizing that, one of the things we did is when we built Express Brokers, we eliminated storage management. What we operated with is really started with not having any storage configuration. Just tell us your retention period, and we are off to the races. You get virtually unlimited storage capacity per broker, which means you really don't have this conceptual notion of what a disk full looks like. Your storage is provisioned per cluster versus per broker. And that obviously has cost savings, but equally importantly makes it easier to sort of imagine what your overall workload size is. And then you pay for what you use versus needing provision capacities. And last but not the least, you get hands-free and instant scaling on the storage side, and that is also super useful. So if you really look at sort of the core tenets of how we worked on storage management, if you think about it in the Express context, our focus was we wanted to eliminate storage management for you, and that entailed doing all these 5 things. The other area that we see where customers are challenged with is around failure handling. So you say, well, what does that mean? Well, here what we have is a 3-broker cluster. You have producers, you have consumers in the consumer group. The producer is producing to 2 brokers here. So what does the basic traffic look like? You have producer traffic, you have consumer traffic, you have replication traffic, and depending on your workload, you have partition compute needs, right? Very rarely we do encounter workloads, or I guess not so rarely, we do encounter workloads that are partition bound, and so you have to account for that as well. And this is the basic configuration that as customers you need to account for, which is what's my producer traffic, what's my consumer traffic, what's my replication traffic, and what are my partition compute needs. And then failures happen. Let's say a broker dies. What happens in that case? You need buffers for handling broker failures. How does that look like? Your producer swaps, your replication switches, your leadership changes, and then the broker comes back, which means your first broker has to actually account for the throughput of 2 producers, right? Now your broker comes back. And now there's different workloads that you need to account for. What is your catch-up replication? What does that look like, right? And eventually, then as the broker rebalances and producer reswitches, you also need to account for what happens when there's a consumer rebalancing. And this is some interesting new innovation that is happening in the Kafka space around us. But all of these are things that you have to build in when planning your workloads. too often, we encounter customers who have workloads that work fine when things are going fine. But when failures happen, that's when they encounter problems. And these are some things that we ask customers to sort of think through. What does your failure handling actually look like? But failure recovery is also time-taking. So it's not just about having the space and buffers to actually account for these failures. It's also accounting for time. And specifically in this case, what happens is, in the standard Kafka case, you're scaling compute and storage together. And especially after a node recovers from failure, it has to catch up. This process is time-consuming, but it's also non-deterministic. What does that mean? It's dependent on what is your storage throughput, what is your storage capacity, what is your compute to local storage network throughput. So you have all these different factors that are sort of competing for attention in that infrastructure, which means your recovery time is going to be dependent on that. Interestingly, Kafka is a remarkably stable system until failures happen. And at the point that failures happen, then the thing that you can do as customers is to wait for recovery. And that often is where a lot of our customer conversations happen, is around how have you thought about failure recovery and failure recovery in these modes. On the Express side, looking at that, what we ended up doing is really rethinking how failure recovery happens. Because we separated our resources, what that means is your recovery is up to 90% faster, right? And that fundamentally means that you're getting higher resilience because your mean time to recovery is low. And that is a phenomenally important thing when you're designing resilient distributed systems, is how do you keep your recovery time low so that you can build resilience for your systems. And that's, I'll walk you through some examples of what that looks like, but that is how Express Brokers is different. What does that mean for horizontal scaling? Everyone has a plan until they have to rebalance partitions, right? And that is what Kafka horizontal scaling looks like. You add 3 brokers, you're going to go move partitions across. You have to reserve enough bandwidth for rebalancing. You have to carefully orchestrate the movement so that it does not impact your existing workloads. And last but not the least, you're continuously monitoring your infrastructure so that if there's a need to change the plan, you can. And that's what happens. Rebalancing can take hours, and again, is variable. And that is how the system behaves. On Express Brokers, because we have separation of resources, what that fundamentally means is you can get up to 20x more elasticity compared to standard brokers. I often get this question from customers, which is, what does elasticity mean? So let's look at an example. How fast can I rebalance my partitions after adding brokers while traffic is still climbing? Here's an experiment that we ran. We had 3 brokers, one topic, 2,000 partitions, 4 terabytes of data per broker. What we did is we had 3 brokers, and we added 3 brokers, rebalanced 1,000 partitions. All this while producing 90 megabytes per second. Pretty typical for what we see. And what we did is compare standard to Express. And I'm just going to show you a couple of CloudWatch graphs. So here's what standard looks like. You have 3 brokers that are at the top. On the left red line is where we issued the command to add 3 brokers. You can instantly see the throughput drops. And the throughput drops and continues dropping, and eventually the new 3 brokers start to pick up. And you can see the throughput sort of gets throttled further, and eventually the throughput stabilizes and behaves as if it's 6 brokers, right? So you get producer degradation until the throughput recovers, and that entire process takes about 175 minutes, right? And so you are going through this partition rebalancing and adding 3 brokers until you get productive 6 brokers for about 175 minutes. Here's what this looks like for Express Brokers. The left is where we added the 3 brokers. Yep, the brokers went to the new throughput, And within 10 minutes, the remaining 3 brokers were added, and they joined the cluster and produced the traffic. Again, from a customer standpoint, and for you as users of this, what that means is you're spending less time doing partition rebalancing, which is giving you a more resilient system, which also means you can scale up and scale down faster. You can run this experiment and see what your results look like. But wait, there's more. What we announced a few weeks ago for Express brokers is intelligent rebalancing. What we've now done is you get always-on rebalancing, you get auto-partition placement, you can do fully automated horizontal scaling with zero-click automated heat management. And that gives you improved price performance from a cluster standpoint. And here's what intelligent rebalancing looks like. You get up to 180x faster rebalancing, which means shorter recovery windows and higher resilience, and that is as compared to standard brokers. One of the interesting things the team did, which really is sort of well thought through, is you get built-in operational awareness. In other words, we detect when there's healing going on, when there's patching going on, and we prevent unsafe overlap. And last but not the least, we apply all our best practices for scale-in and scale-out intelligence before resizing our clusters, right? And so that becomes enormously helpful in terms of giving you a signal of what workloads your brokers can accept. So super happy that this is in customer hands. It's available for Express brokers and it's starting, I think, 2 weeks ago. So one of the other things was we had to rethink what resilience looks like. And part of this is to help you understand sort of how we think about resilience and all the work that we had to do to sort of build in resilience. Here's what standard Kafka behavior looks like. You have a broker, I sort of modeled it as you have a broker with partitions, you have memory, you have compute, you have network, you have storage. Kafka classically is an allocate when asked system. You sort of can request capacity, it'll give you capacity. You can create a partition, it'll create a partition. And what happens is the onus is on Kafka clients and the users to not overload the system. And the challenge with that is you only find out you've overloaded the system by monitoring it well, by having heuristics, by having experience of managing your workloads. But when that overloading happens, it causes broker failures. And so you are in the mode of recovery at the point that you've overloaded the brokers. So one of the things that we did in Express is you have the same model for a broker, but for each of those, we have added safe throttles, safe dynamic throttles on compute, memory, and networking. And what that means is we can start to minimize sort of the impact on the broker and protect the broker from failures. In fact, the team has also had to think through what does it mean to survive storage failures. Now, you can't survive storage failures for an infinite amount of time, but still, it builds in resilience and gives you the capacity, at least for a while, to survive without storage being there. And last but not the least, especially as we throttle, your client can then react to the throttling behavior it sees instead of just seeing the failure and then reacting to the failure. So what that means is, from a design standpoint, you actually have the ability to design your system to take cognizance of the system being overloaded and actually accounting for it differently. And that is something that is fundamentally different about what we had to do in order to re-architect for resilience. So it goes further deeper. One of the other things that we did with Express is we made it such that you did not need a maintenance window for patching. We also built in partition level fairness. And what does that mean is you get protection from noisy workloads. So you can't have a single partition taking up all the throughput of your broker, and you get better protection on that. Last but not the least, one of the things that the team has also had to think through is what does it mean to stop potential cascading faults, and how do you isolate them by design? Nothing's perfect, but there's a lot of thinking that had to go in terms of building systems that can survive. And so part of like walking you through this is to help you understand what does it mean to actually operate and run these systems at scale. Now, there are some customers who will come and tell us, we want even lower management. And so all of this infrastructure and all of that knowledge we build into MSK serverless, and there you're just operating at the level of scaling up, scaling down. You're doing zero Kafka management. And normally we recommend it for new to Kafka or new to streaming customers. I debated putting this slide up, and I debated very, very deeply about like, this seems remedial, and yet it's one of the more common failures that we see with customers is monitoring Kafka. What I'll show you on the next slide will seem obvious, but it's remarkable how customers, like a lot of customers are not set up for actually monitoring these. So these are the things we recommend you monitor on your Kafka setup. So I'll start with the per broker, per cluster things. It's partitions per broker, total partitions per cluster. It's connections per broker. Monitor these, right? It's super important to make sure that these are within the bounds, and in fact, set alerting so that you can react to this. And then on the usage side, think about your broker CPU usage, your disk usage, your memory usage, your throughput usage. It is amazing how these simple metrics will give you a view on what it means for the service and the system to operate. Super important that you balance not just the operational side of running the system, but also the monitoring and making sure that you're doing the right thing. That is what it means to run Kafka at scale. Up next, Sai will tell you about what it means to run Flink at scale.
Well, thank you so much, Ashish. So now that you've got all the data streamed in Apache Kafka, you need to process it. And that is where running Apache Flink at scale comes to fruition. So how many of you have some of these use cases, anomaly detection, where you're transforming data before you're loading that into an OLAP system? How many of you are supporting building event-driven applications? If you're using any of those use cases, or all those three use cases, then you should be using Apache Flink. There are 4 reasons why. First, it's real-time. Second, it's great at handling dynamic data sets. Number 3, it's stateful. And finally, it is programmable. Let's dive deeper into each one of these using an example. Imagine you are building a fleet monitoring system, and your goal is to detect anomalies as quickly as you find them, so that way you can improve the customer experience. So let's start with a few nodes, and within no time, my fleet grows, and now I have tens and hundreds of nodes, and in no time, I have thousands of nodes to monitor and detect. What is equally important to remember is, as your customers are creating new resources, you have new nodes to monitor. And when they're deleting resources, you no longer have to monitor those nodes. So this set of data that you're monitoring changes rapidly. Somewhere along the line, you realize that, look, my anomaly detection can be better if I also include storage monitoring into the mix. And then eventually software versions, regions. So very quickly, what you see is a big increase in complexity for your data. This is where Flink's continuous processing is a lot better than using batch-based processing. A batch is like capturing a photo. A photo captures what's true in the moment. You cannot track what happened before or potentially what has happened after. Comparatively, a video captures every frame, every detail. It gives you all the rich context available for you. You can go pause that, go back to a point in time, compare different things, and get to the insight in a more accurate fashion. We also talked about one of Flink's strengths being its stateful. So in our example, you're able to capture the state per key, per server, per software type. And as new events come in, that state is incrementally updated by Flink. And what it does, it waits for patterns to emerge. And either decides, well, this is noise, so I'm going to suppress it, or it's a valid signal, let me act on it. So in our example, it could be a a breach in threshold where you say, well, I want to monitor if I have more than 5 faults in any given minute. And if it breaches that threshold, I want to trigger an automated action, which is replacing that faulty node before the customer is actually seeing impact. So being stateful gives you that rich memory for you to make more context-aware decisions. The last piece is it's programmable. So in our example of fleet monitoring, you can start with a simple if-then-else logic. If this happens, I'm going to do this. But over time, you realize, well, I want to also monitor my storage. So you can evolve your logic to now also include other metrics. You can also map the data to a table in a database table so that you can actually enrich that context. And finally, you can start with simple actions. In my fleet monitoring example, that customer started with creating an alarm so that a human can react to that alarm and replace that node. But over time, they grew confidence in operating that system and started taking automated action using that workflow. So this gives you that ability to constantly evolve your application. The combination of real-time, statefulness, being able to handle dynamic data sets, and programmability is also the reason why customers are turning to Flink to build agentic AI applications. So what does it take to do more data processing workloads real time? When we talk to a wide variety of customers, 3 particular patterns emerge. First, it requires a change in your operating model. Second, you need resilient Flink infrastructure. And finally, build programming logic that is robust. It sounds obvious, but it's very important. Let's start with what do we mean by change in the operating model, and a good way to understand that is to compare that with batch-based processing, something that is popular, has been popular over the years. In the batch world, your data is largely fixed. So you're processing data that is either a day old or a few hours old, and the analyst is now running different set of queries to find that insight, and then essentially also leaning on a human to generally take an action. Comparatively in a streaming system, data is getting continuously generated. And then what is happening on this set of continuous generating data, you're applying a set of generally static rules to understand insights and almost automate the action. So in our fleet example, the automation there is replacing that faulty node or storage device. Time is explicit in the batch world. When you take a photo, that the snapshot tells you that this was taken at this particular time. But when it comes to video, you have to specify that time explicitly. I want to go to this particular time frame and then compare things. So time is explicit in streaming systems. So that is what we mean by changing operating model. You're moving away from dynamic queries on static data to static queries largely on dynamic data. That also means that as developers, there are some new concepts for you to learn. First is event time, which actually tells you when the actual event has happened, not when it's processed. Sometimes, as an example in our fleet monitoring system, you could get events related to storage before you get events related to server. If you end up using processing time, you would miss processing events related to your server. And that means your action would not be accurate. So leaning on event time becomes very important. The second key concept is Windows. Because you have this continuous flow of data, Windows allows you to group these events into small buckets for analysis. The next important concept is partitioning. That essentially is how data is distributed so that you can parallelize your processing. Now, because Flink is trying to process data at really high throughput, low latency, partitioning becomes very important. Lastly, one of Flink's strong calling card is its support for exactly once processing, which means that as a developer, I get the confidence that I'm not worried about duplicates when it comes to processing. So I'm processing each event exactly once. So how does Apache Flink support high throughput data at low latency with remarkable consistency? The answer lies in its architecture. The job manager is like the brains of the Flink system. It is planning, scheduling, coordinating the work. And then you have task manager, where the actual processing is happening. And the task manager is further broken down into task slots, which aids for parallel processing. So here's how it works. So you deploy, you build your logic, you deploy it as a jar, and then job manager takes the code, first translate that into a logical unit of work, and then breaks that into physical units of work and places those work in task slots. Why? Because it wants to guarantee parallelism. Flink also captures the state. We've talked about how important that is, and periodically checkpoints its processing into a durable storage within S3. And the reason it's doing that is to give you the guarantee of exactly one's processing, but also be resilient when failures happen. So when a job fails, when infrastructure fails, it needs to know where to start and how to start those operators processing data again. So this combination of orchestration with job manager, parallelism driven by task manager, as well as checkpoints, give you the right set of primitives for you to run at scale. But as an administrator, what are all the activities I'm responsible for to run these systems at scale? They largely fall into three categories. First is deployment, second is monitoring, and the last is scaling and evolution. So your developer comes to you, they want to build an application. So the starting point is you pick an infrastructure provider, a Kubernetes-based system. Then you have a choice to make, whether you want to run that in application mode, where you have a dedicated set of infrastructure for that job, or you want to run in session mode, where you can run multiple jobs on that same set of infrastructure. And for most at-scale applications, you choose the application mode. Then we're off to monitoring once you've deployed the infrastructure. And we'll go dive deeper into this subject. But the core goal there is to make sure that you're always processing data. And finally, scaling the system is super important. And we've talked about how programmability and evolution are so key primitives for Flink. And so your goal there is to monitor when you need to scale, do the scaling event, also support deploying new code. So that's what it looks like as a life cycle of a Flink job and the activities around it. Now, for developers running applications, this is a fairly involved process. So at AWS, we offer managed service for Apache Flink that provides the easiest way for customers to build resilient Flink applications. So the developer experience with our managed service is far simpler compared to the deployment example that I gave you before. So in here, there's no infrastructure setup. You get built-in multi-AZ resiliency, and there is no configuration tuning. And here is how it works. You go to your favorite IDE, build the application, get a jar file out of it, create an application within the managed service, and then you're off to the races to start processing data. There's no compute to manage. There's no configurations for you to set up. Now you've got this thing up and running. Now you have to operate it. And what I'm going to do next is kind of walk you through our learnings operating Flink applications at scale and how you can potentially benefit from it. And I'm going to focus on two specific learnings. The first one that we've learned is in Flink, a significant change can lead to processing being interrupted. So what is a significant change? Could be you're trying to scale the system. Could be you are trying to handle a node failure. Or it could be you're doing patching and software upgrades. In each of these cases, what happens is Flink says, OK, well, I detect a change in the system. Let me pause everything. Let me reassign things, and then resume processing. So our first goal in operating the system is making sure that we're minimizing these processing delays. How do we do that? The key to do that is to separate the time it takes to spin up EC2 instances and other prerequisites from the overall job downtime. So you separate those things out. And we do that with two specific techniques, which is one is blue-green deployments, the other is having a warm pool. With blue-green deployments, we do not stop the job until we set up and verify the prerequisites. Here is how it works. First, we spin up the necessary EC2 instances. Next, we verify your job configuration. We'll make sure all the prerequisites are met. And at that point is when we are switching over from the old infrastructure to the new infrastructure and resuming processing from the exactly same point at which you stopped processing previously. The next key concept is warm pools. So instead of waiting for EC2 instances to spin up and the amount of time it takes, we maintain a warm pool of infrastructure. Thereby, we get an instance that is ready to go. So the combination of blue-green deployments and warm pools is how we reduce the time and how we reduce the job downtime when there is a change in the system. Another key aspect that we've talked about is how Flink allows you to change and evolve your logic. So our fundamental goal is to how do we make this whole process simple for our developers or for our developers. We want it to be repeatable, fail-proof, and quick so that they can consistently make changes. So how does this work? Well, a developer decides that they want to go make changes, build a new jar file with their code changes, and they submit to the managed service. And what we detect that there's a new deployment that is happening, and we do not stop the job right away. We take a snapshot of the current running job, durably store that in S3, and then the managed service sets up this new job with the configuration, sets up the new infrastructure, including EC2 instances, make sure they're spinned up and they're running, sets up the job configuration, validates the things, and then restores the state from what it has stored in S3. So now your operators are running with the preserved state. And that is when you switch over to the new infrastructure and you resume processing. We also pair this with smart guardrails. The goal there is to detect any known code issues, and thereby it doesn't impact job processing. So the way this guardrails work is, as an example, imagine you upload a new code and that has some null pointer exceptions. It detects that this code is having issues. It automatically reverts back to the last known good state of this application and starts to resume the processing. So a combination of automation and the orchestration of how we deploy new code, blue-green deployments, and smart guardrails is how we give developers the confidence to constantly evolve their applications in a highly resilient way. The second learning, the first learning that we talked about is any change in Flink means there is a job downtime and how do we minimize it, right? The second key learning we've had is a lot of times developers and administrators in Flink are working with different abstractions. Developers are thinking about code, logical operators, and then admins are thinking about resources, its utilization, and they have no visibility into the code. And same way, developers have no visibility into the actual infrastructure. So we recognize there is a need for them to have a common mental model and how to reason about Flink. And there are two key shared mental models that we recommend customers. First is fixed unit. The second is how do we think about job availability and not just infrastructure availability. Let's talk about fixed units. Typically, it's very hard or very unpredictable to map the Flink code to the actual resources like task managers and task slots. It's very unpredictable, hard, complex. And the reason is that different task managers can have different performance characteristics, and depending on how you've created slots, that can have different performance characteristics. So you have a pretty unpredictable system. And the goal with fixed units is to bring predictability into the system. So in our managed service, the smallest unit of provisioning is a KPU, which gives you a 1 vCPU, 4 gigabytes of memory, and 50 gigabytes of storage. So what it does is now you get deterministic performance per parallelism. Each lane is also isolated, so the trouble with noisy neighbors is no longer an issue. It also makes debugging easier. So when you have hot slots or issues, it's very easy to detect where exactly it is happening as an administrator and resolve that very quickly. Lastly, it simplifies scaling. So if you want to add more capacity, you simply add more parallelism units. And then you also get predictable state slices. So things like checkpointing and back pressure management becomes a lot more consistent for application admins. So what does fixed units do? For developers, what it means is your workflows are simple. Now you can design your code so that they fit in a fixed budget. And then once you figure out what that deployment profile looks like, then you can scale that by simply adding more KPUs. And for administrators, by enforcing these guardrails, you are being more proactive rather than being reactive when it comes to handling issues. So that is the role of the fixed units. The second common way that you want people to reason about Flink is to think about job availability rather than infrastructure availability. Now, job availability tracking in Flink is very hard. Flink states whether the job is running doesn't always mean that data is getting processed. Why is that the case? There are 3 reasons why that may happen. First is the boundaries between user code, Flink runtime, and external systems are all not always clear. So debugging is very complex. Second is restarts and recovery means a lot of times the underlying root cause is masked. The second run, which starts producing different errors, will mask the errors that were actually caused by the original problem. That makes troubleshooting very hard. Finally, issues can happen that are external to the Flink runtime. Think about node failures, storage failures, so it's important to track them and address them. So what we recognize is we need a smarter detection system, a system that can detect that there's an issue, classify it, and be very surgical about the action it's trying to take. So what we built is a system that consistently monitors a Flink job, looks to classify whether an issue is something that is related to user code or is a system-driven one. A user-driven issue could look like issues with your code, like a null pointer exception, things that have resource exhaustion that is created from the code base. A good example of that is you've opened too many connections, you've not closed them, or it could be incorrect configurations that you've picked for your job. All of these are in the category that are related to user code. And then you have system-related issues. And these could look like node failures, Flink bugs, or generally issues with connectors. The automatic healer identifies these error causes, classifies them, and then the reason the classification is important is it can be very surgical about the fix it wants to do. As an example, if it detects that there are incorrect configurations, dynamically it can change those configurations, and thereby restart becomes much faster. And the whole purpose of the system is to reduce the mean time to recover from the failure. Let's dive deeper using a few examples. The first one is performance degradation. Imagine you have built an application, for the fault system that I talked about previously. It works great for 100 records per second, 100,000 records per second. But now suddenly you want to scale that to 500,000 records per second. And those specific static configurations that you picked no longer work for this increased scale. And Flink gives you 400 plus configurations to choose from. And that makes the whole process harder. So what the detection system does is it detects that there is an issue with the incorrect configuration, fixes that dynamically, and thereby recovers the job very quickly from the performance degradation. The second example is something that we see very typically is with connectors. A good scenario for this is Flink is looking to restart the job to recover from another failure. And then what it realizes is that there is this process related to this connector that is not responsive. So what the detector does is it detects that there's an issue with this connector process, kills that process externally, thereby the job can restart very quickly. Here's an example, once again, where the goal is to recover faster from an issue. Finally, failures can happen outside the Flink job, which we've talked about. A good example is node failures. Failures do happen. Infrastructure does fail. And when it fails, we detect that there's an issue, pick a node from the worm pool that I mentioned previously, and then accelerate the recovery process very quickly for customers. So again, 3 examples where having a detection system, classifying it, being very surgical with what we're fixing, reduces the mean time to recover from failures. Now, what we've also recognized is availability is also the function of your code. Issues such as high CPU, out of memory, disk throttling can also come in terms of how the code is structured. Let's understand this using an example. Imagine a developer says, look, I have this high CPU issue. And you start dive deeping into that job graph, and what you realize is that job has morphed itself into a wide variety of subtasks, 1,600 plus subtasks. And they're trying to fit that into 10 KPUs. Now, one way to solve the problem is to horizontally scale, add more KPUs, and you're almost like throwing money at the problem. The other way to do that is to look at, is the code structured properly? A couple of ways to think about that is, one is there excessive branching happening in this code? Now, back to our fleet monitoring example, one way to branch is by alarm type. It's almost like I'm executing the same logic, and I want to execute that for each alarm type. So I have 20 alarm types, I have 20 branches. Another way to do it is, hey, is there something that is common across these 20 branches? And potentially you can organize that by window sizes. You could have 1-minute windows, 5-minute windows, and maybe 3-minute windows. So you can go from having 20 branches to 3 branches. So instead of throwing infrastructure at the problem, you are reorganizing the code so that way you have lesser subtasks, and there you can fit into the 10 KPU that we've talked about. Another example is parallelism. Sometimes what you see is not all task managers are busy. There are some that are running extremely hot, and there are some that are idle. And that means that you've picked an operator parallelism that doesn't work well consistently across the entire pipeline. And that is a case where you could work with the developer to make sure they are very specific about the operator parallelism they're picking across different parts of the job. So these are a couple of examples where how you lay out code can have an interesting side effect on the infrastructure. So what it comes down to is you need another layer of defense to make sure you're detecting these issues very quickly. Now, Flink gives you a raft of metrics, and I'm not going to spend time walking through every metric, but what I want to share with you is a mental model around what our customers use when they operate Flink at high scale. The first category is application health. And the goal here is not just the actual uptime, but also more importantly, is the job making progress? Because at the end of the day, it's all about processing data. The second category is checkpoints. Checkpoints are Flink's safety net to recover from failure. So you want to have a robust monitoring mechanism for these checkpointing data. So you're looking at things like, is the duration of checkpointing long? Are the sizes pretty high? So you want to make sure that system is very robust. The third important monitoring area is latency. At the end of the day, Flink is a real-time system. And you want to make sure you're always processing the freshest data. And so one way to do that is to compare your watermarks and see if they're slow or fast. A slow watermark means there is lag getting built up, which means that eventually you have stalled task managers. So the goal there is to compare, as an example, your watermarks with your processing time to see how behind you are with the latest data that is being processed. The fourth dimension is throughput. Not just the aggregate throughput, that is easier to monitor, but also to monitor throughput to make sure there's not enough back pressure being built into the system. Because say, as an example, there's one part of the workflow that is getting backed up, then what it means is that spreads across the entire pipeline. So the goal of that is to monitor throughput at the operator level, at the subtask level. Thereby, you have the insights on where exactly within the pipeline you're having those back pressure challenges. So those are the four different categories on how you can build a robust monitoring mechanism for your Flink applications. You also want to understand what are some of the best practices that we can share with the development teams. One of the successful patterns we've seen with customers is where they've democratized this on how to build Flink applications into their enterprise. So what does a good code and behaviors, and when it doesn't, and what does the anti-patterns look like on infrastructure? The first area is timers and watermarks. Now, we've talked about how event time is super critical. And so when you don't use event time, you end up using processing time. The typical complaint you see is, well, my aggregations are off. Well, that tells you that somewhere in the code, people are using processing time versus event time. Another scenario is with timers is your watermarks are slow. So if your watermarks are slow, it means there's too much lag. What if they're too fast? Well, if you're too fast, you're not waiting long enough for data that is trickling in slowly. So you need to find the right balance between fast and being too slow. The second area is state hygiene. And again, state is such a crucial aspect of Flink, but you don't want to keep everything in that state for all the time. What you want is to enforce TTLs, thereby you're evicting state as and when it's necessary. So getting your state management is super critical in your code. The third big area is avoiding data skew. One of the calling cards of Flink is how you're able to partition the data, process each of that chunk independently, and you do that by using key-by operators. Now, what type of operators, what type of data patterns you want to use? You certainly want to avoid low cardinality keys, because what happens with low cardinality keys is you have some task managers that are running hot and some task managers that are running inefficiently. So you want to pick a high cardinality key each time. Also, you want to reduce the number of shuffles you do. Shuffles are critical because you want to shuffle data because you want to get data based on one particular key, process that data differently. So you would end up using shuffles, but using too many means data is getting shuffled too much. That also impacts how much time is spent on serialization, and that leads to CPU being busy, garbage collection being slow, and things of that nature. Lastly, serialization and schemas play a very pivotal role. Not all use cases would benefit from the default serialization. And when you end up using the default serialization, especially for CPU-intense workloads, by doing transformations and complex transformations, that ends up, again, being an infrastructure issue. Schemas also play a very important role. Instead of getting all the data, then validating it for the quality, schemas allow you to enforce that on the producer side, so that the Flink consuming code is confident that the data that it's getting is actually qualitative enough. So in summary, writing the optimal Flink code will make sure the applications are fast, resilient, and reliable. So that brings us to how and what it takes for us to run Kafka at scale. Now, if you want all these capabilities without the overhead, we offer our managed services. So I want to bring Ashish. Ashish, we've talked about what it takes to run Kafka and Flink at scale. What are some of the top key takeaways from this?
Yeah, I think it's a really pertinent point. One of our motivations in doing this session was actually sharing our experience. And a lot of the discussions that I know Sai does as well, and I do, are about customers who know Kafka, but at the same time, the effects of scale when they encounter running at scale or when they encounter failures at scale are different. And one of our learnings from that was oftentimes the only place that you actually learn about failures and how you handle them is when failures happen. And that's probably the worst time to actually learn those failures. And so what we've tried to do is explain some of our thinking in terms of our best practices, but also explain how we are building the system ground up to make sure that these things are accounted for. You saw this on the Kafka end as we transition from standard to serverless to express, and you're seeing this on the Flink end on how we are applying that. Part of why we are sharing this is so you, as you are making your choices about running your infrastructure, are able to make a decision on which of these to apply, how you'll apply it, and how you'll run it. The last piece the last sort of big takeaway from me, and definitely looking for learning from you on the Flink side as well, is too often customers are running infrastructure but actually not monitoring the things that can cause the failures. And so what happens is oftentimes when failures happen or the SOPs are not functional, then what happens is you discover that your system is not running as stably as you thought. And a part of this is that there is a shared responsibility boundary in terms of managing the infrastructure, which we will do and we will own, and equally importantly, managing the operational side of Kafka or Flink, which then you and us as customers have to participate and partner on. And that side is my key takeaway. Partly what I'm hoping here is that we can help customers as they're thinking about their choices run better systems. Anything on the Flink side that you'd like to add?
It's very similar to what we've spoken on Kafka. I think the three things are like knowing your shared boundaries. Now with Flink, the shared boundary also means you're running code, arbitrary code. So that has an interesting effects that we talked about. Second is picking the right offering, right? And sometimes you can learn from our best practices, our learnings that we built into our products and build infrastructure on your own or use some of our services. So that I think it's very similar to our learnings on Kafka side as well. Awesome. Well, that brings to the end of the presentation. Now, you can try it for yourself, both MSK Express brokers as well as deploy your Flink applications on our managed service for Apache Flink, because at the end of the day, seeing and trying is believing.
With that, thank you so much.